colligative properties is going to be the topic of this lesson. And we'll start off by talking about what the Van Hoff factor is and how to look at a compound and figure out what that Van Hoff factor is going to be. And then we'll move on to four major colligative properties, which are properties that are going to vary as the concentration of solute in a solution varies as well. And that's going to be freezing point depression, boiling point elevation, Raoult's law for vapor pressure depression, and then finally osmotic pressure. We'll do calculations for each, and we'll look at some common pitfalls. And by the end of this, you are going to have a much better handle on colligative properties. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You can find those courses at chadsprep.com. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. All right, so colligative properties, and again, these are properties that vary with solute concentration. The more solute you add, the more these properties are going to change. And so the first one we're going to hit is freezing point depression, or same thing as melting point depression. It turns out that the melting point of a solution or of a particular liquid is not fixed. As you add more and more solute, it actually goes down. And the more solute you add, the more it goes down. And it turns out it's largely independent of what solute you are adding. But the more solute you add, whatever that solute is, the more it's going to go down. And so the identity of the solute is not key. It's just how much of it you are adding. And it turns out it's really related to how many particles are going to be present in that solution. The more particles of solute there are that are disrupting some of the intermolecular forces that would normally be going on with that solvent, the more it's going to change these colligative properties. So it turns out that we have to talk about what's known as the Van Hoff factor, which takes into account that electrolytes often dissociate into multiple ions. And again, if all that matters is the overall number of particles, well, then this is going to directly impact the overall number of particles, and is something we definitely got to take into account. And so this Van Hoff factor for strong electrolytes, it's just simply equal to the number of ions a particular strong electrolyte dissociates into. So if we take a look at NaCl, for instance, so NaCl is indeed a strong electrolyte, and a reminder, those strong electrolytes are either soluble ionic compounds, which is NaCl, or strong acids or strong bases, which we had to memorize back earlier in the course. And so in the case of NaCl, when it dissociates, you get one sodium and one chloride, a total of 2 ions. And so the Van Hoff factor here, we say, is equal to 2. And we use this little lowercase I for that Van Hoff factor. Now, barium hydroxide is a strong base. And in this case, your strong bases were LiOH, NaOH, KOH, RbOH, CSOH, BaOH2, SrOH2, and CaOH2. And in this case, when it dissociates, you get 1 barium, you get 2 hydroxides. That's a total of 3 ions. And so the Van Hoff factor would equal 3. All right, now non-electrolytes, on the other hand, they have a Van Hoff factor of 1. They don't dissociate to give any additional increase in particles or anything like that, but they themselves are particles. And so you might recall that your non-electrolytes are typically molecular compounds that are not acids or bases. And so in this case, your molecular compounds are made of all non-metals, and this is methanol in this case, carbons, hydrogens, oxygen. And it's not an acid or base. It doesn't begin with like an H in the formula, like HF is a molecular compound that's an acid. Well, in this case, this is a molecular compound that's not an acid or a base, and it's therefore going to have a Van Hoff factor of just 1. No increase again no increase in the number of particles due to dissociation or anything like that. So last but not least, we've got aluminum nitrate here, and I wanted to use one with a polyatomic ion because it's not necessarily the number of atoms something dissociates into, but the number of ions. And you got to remember that like with something like aluminum nitrate, you're going to get aluminum ions, but you're also going to get nitrate ions. But the nitrate ions themselves don't break apart into like nitrogens and oxygens and things of this sort. And you're going to get 1 aluminum ion, but you're going to get 3 of these nitrate ions for a total of 4 ions. And so for aluminum nitrate, this Van Hoff factor equals 4. And so it turns out, if you've got, 1 mole of methanol in water and 1 mole of aluminum nitrate in water, well, with the aluminum nitrate, you'd have 4 times as many moles of particles and 4 times the change in whatever colligative property you might be looking at. So that's why these directly affect the number of particles in solution and are going to have a huge impact on how we look at these and calculate these colligative properties. Let's take a look at these colligative properties. So the first 2 colligative properties we're going to look at together here are freezing point depression and boiling point elevation. And it turns out the more solute you add to a particular solution, the more the freezing point's going to drop and the more the boiling point's going to increase. You might say the boundaries at which it's a liquid are going to expand at both ends. And here we've got a couple of mathematical formulas that look very similar to how this works. Now, one thing to note, these are my formulas that I've given you, but much more commonly, you're probably going to see them presented a little bit different in your textbook. And so you might see that the change in your freezing point just equals Kf times m, and the change in your boiling point just equals Kb times m. Well, Kf and Kb here are just constants for your particular liquid. We got a freezing point constant and a boiling point constant. And for example, the freezing point constant for water is 1.86 degrees Celsius per molal. So for every molal of particles you have, freezing point goes down by 1.86 degrees. If you have 1 molal, then it drops down below 0, the normal freezing point, by 1.86 degrees. Another molal drops down another 1.86 degrees. On the other hand, your boiling point constant here is 0.51 degrees Celsius per molal. And so in this case, again, you got to remember that boiling points go up. And so if you've got a 1 molal of particles in your solution, the boiling point's going to go up over 100 degrees. Again, that's the normal boiling point for water. So in a go up for 1 molal, it go up by 0.51 degrees, about half a degree. Another molal, meaning another additional 0.51 degree increase in that boiling temperature. And that's the way this works. Now, you're going to take and multiply, therefore, your constant by the overall molality of particles according to these equations. Now, to get that overall molality of particles, we got to be a little bit careful here. So that overall molality of particles is going to factor in if it breaks up into multiple pieces, because it has a Van Hoff factor that's not 1, if it's an electrolyte of some sort. And really, that's going to be I times m in my equation. So in this equation, it's the overall total molality of particles, and you have to remember to take into account that Van Hoff factor. Whereas personally, I just like to incorporate that Van Hoff factor right into the equation, and then you're just using the molality of the solute as it is. So same thing with the boiling point as well. Now, one thing to note, you've also got to remember that freezing points go down. In the standard equation that's often presented, they don't put the negative sign out front. They just expect you to remember that it's freezing points that go down, whereas boiling points go up. So I like to incorporate that negative sign right in there. That way when we calculate the change in our freezing point, we get a negative change, and that implies that it goes down. So my personal favorites on the equations here. So if you see it presented a little bit differently, that is why. And you can take your pick at what you want to do as far as that goes. If your book does go with these two versions, just notice that that's likely to be what's on any kind of equation sheet you're provided with. So keep that in mind as well. But I will be using these two versions of it right here. Okay, so a couple different kind of questions you might get on something like this. And before we do any calculations, though, we're going to see some questions you might see that don't involve any calculation whatsoever. And so first one here is, which of the following aqueous solutions here would have the highest boiling point and highest freezing point? So we really got two questions here. So first, highest boiling point. Well, again, boiling points go up. And the greater the overall concentration in solutes, the more they go up. And so the overall highest boiling point is going to be one that's gone up the most. Let's answer that question first. So in this case, you might be given all equal concentrations, so of 4 different solutes, and it's all then therefore going to come down to that Van Hoff factor. So the molality, is the same in all cases, but it's the Van Hoff factor that's going to be the deciding factor. And so if we take a look at this, so in this one, NaCl, we said the Van Hoff factor was 2. For methanol, it's a non-electrolyte, so the Van Hoff factor was 1. Barium hydroxide, a strong base. Van Hoff factor was 3, 1 barium, 2 hydroxides. And then finally, for aluminum nitrate, 1 aluminum, 3 nitrates, total of 4 ions. The Van Hoff factor was 4. And so for the highest boiling point, we can see that that's definitely going to be aluminum nitrate. So he's the one that's going to go up the most, and therefore end up with the overall highest boiling point. Now, for freezing point, it works a little bit backwards. So freezing points go down, and so the one with the lowest molality will go down the least. And the one with the highest overall molality of particles goes down the most. So, but in this case, the question wasn't which one's gone down the most. The question is which one has the highest freezing point. Well, the highest freezing point is going to be the one that has gone down the least. And so in this case, a little bit of a tricky question. We talk about freezing points. A lot of students will get this one exactly backwards. But if you want the overall highest freezing point, well, then you want the one that's gone down the least and therefore has the lowest overall concentration of particles. And in that case, this would be the methanol with the smallest Van Hoff factor. And so the aluminum nitrate has the highest boiling point, but it's the methanol solution here that's going to have the highest freezing point. Now, if I said which one has the biggest change in either boiling or freezing point, doesn't matter which one, but the biggest change, well, that's going to be the aluminum nitrate in both cases. If I said which one has the smallest change in either freezing or boiling point, that would be the methanol in both cases. The trickery comes only when we talk about highest freezing point, and the highest freezing point was the one with the smallest change. Just keep that in mind. All right, let's see how this, another way this might be phrased as well. So the second way you might see this presented, so very similar question, looking for the highest boiling point, highest freezing point, but now not only do we have 4 different solutes, but they're at 4 different molalities as well. And so the difference really is not just a difference in just the Van Hoff factor, but also in the molality as well. But essentially you can just take and multiply the Van Hoff factor times the molality, and whichever one comes out the biggest, well, you're going to multiply them all by the same either freezing or boiling point constant. And so whichever has the biggest combination of I times M will have the biggest change. And again, for boiling point, that means gone up the most. For freezing point, that means gone down the most. And so in this case, that's what we want to find for each of these. We just want to take I times M. And so for NaCl, his I was 2. He splits apart into 2 ions times 2 molal gives an overall I times M of 4 molal. And essentially what this is, that's the overall total concentration of all particles, all ions in this case. Essentially that would be the same value that you would have put in this version of the equation up here at I times M. For methanol here, again, he's got a Van Hoff factor of 1, and 1 times 1.5 is simply just 1.5. For barium hydroxide here, again, his Van Hoff factor was 3, and 3 times a molality of 1.2 is 3.6. And then finally, for aluminum nitrate here, his Van Hoff factor was 4, and 4 times 0.9 also 3.6. And so we find out that the greatest overall concentration of particles is not the aluminum nitrate anymore, but it's actually the NaCl with an overall total particle concentration of 4 molal. And therefore the NaCl is going to end up with the highest boiling point. So, but he ended up with the lowest freezing point. And again, the question's asking for the highest freezing point. Well, the one that's going to have gone down the least is the one with the overall lowest concentration of particles, the lowest product of I times M, and that's the methanol in this case as well. Cool. So a couple questions they've done, really not the most challenging calculations, or in the first case, not even really any sort of calculation involved, but calculations are coming. And so you might get some calculations that are more plug and chug with the formulas instead of comparisons. Let's take a look at how that plays out. So the first calculation we're going to take a look at is the freezing point of a solution of 1 molal NaCl. And again, being that we're finding the freezing point here, we've got our lovely freezing point equation here. And in this case, we know the Van Hoff factor for NaCl is once again 2. So the freezing point constant I provided here is 1.86 degrees Celsius per molal. So if you were doing this on your homework or something, there's usually tables in the back of your textbook where you might look these up, or obviously you could Google it. But in this case, that's the 1.86 degrees Celsius per molal. And then finally times your molality, which was 1 molal in our case. Cool, and we'll see that the molals here will cancel, and we left an answer in degrees Celsius. And 2 times 1.86, you can do that in your calculator. You can do it in your head if you like. So 3.72, and don't forget that negative sign. And so we're going to get a change in freezing point of negative 3.72 degrees Celsius. And so if we're calculating the change, then we'd be done. That is the change in the freezing point. Well, because the original freezing point for water is 0 degrees Celsius, it turns out that just also ends up being the freezing point too. So to find your freezing point, your new freezing point, which I'll call new in this case, is going to equal the normal freezing temperature plus the change. And so in this case, we'd take our 0 and add in that negative 3.72 degrees Celsius to get an overall freezing point of negative 3.72 degrees Celsius. And you might be like, this seems pretty redundant, Chad. And it is. But the key is this only works out this way because the freezing temperature for water was indeed 0 degrees Celsius. Had we given you some other liquid, it had, say, a freezing temperature of 20 degrees Celsius, well, then you would have been 20 plus the negative 3.72, and you wouldn't have got negative 3.72 for the final freezing point. So I just want to make sure you'd seen it that way. Now, one thing to note on this, You are most likely expected to know that water's, standard normal freezing temperature is 0 degrees Celsius and boiling temperature is 100 degrees Celsius. However, for any other liquid, you probably don't have to know those values. They're probably going to be provided for you. And you probably don't have to know anybody's freezing or boiling point constants. Those are probably always going to be provided for you. But for water, know the boiling point, know the freezing point. For any other liquid, probably going to be provided for you. All right, so this did indeed seem a little bit redundant, but I just wanted to make sure you saw the difference for some other liquid. All right, next question here is going to be finding the boiling point instead. Cool, very similar equation, so just going to have a different constant, and this one's going to be a positive change as boiling points go up. And so in this case, we're going to have 2 for the Van Hoff factor times now our boiling point constant 0.51 degrees Celsius per molal, and then finally times our molality of 1 molal. And so we'll see that our delta T here is going to equal 2 times 0.51, which is 1.02 degrees Celsius. And so if we want our final, which again I'll call the new boiling temperature, let's get a B in there as well. So then we take the original boiling temperature of 100 degrees Celsius, add in the 1.02, and now we're going to have 101.02 degrees Celsius as our new boiling point. Cool, and this is the way this works. Now, we got one last little issue to talk about with this, and the real issue is, why does this work out this way? We've done all the math, we've done all the comparisons, so the question is, well, why does the freezing point go down? Why does the boiling point go up? And the first one's going to be the easier to answer. Why does the freezing point go down? But we're going to need a little bit of room here. So if we look at when a substance freezes, it's going to freeze typically into a nice, lovely crystal lattice structure, a nice repeating structure. And with all the molecules being exactly the same, it's going to fit a nice, regular, repeating fashion. And so what happens when you cool down a liquid, you cool it down, and all of a sudden it's going to lower its kinetic energy. And at some point, it won't have enough kinetic energy to overcome the attractive forces between the molecules. And below that point is the point at which it will freeze into a crystalline solid. Well, what happens when you put some sort of impurity in there, some sort of solute in there, and so you're going to put something with a little bit different shape in there all of a sudden. And so now it doesn't actually fit into the crystal structure in the same way that the original, in this case, water molecules fit, let's say. And so as a result, you're going to actually have to slow these molecules down more than normal to get it to crystallize out, because now we have an imperfection in that crystal lattice. And so because we have to cool it down more, the freezing point is now lower as a result. And again, the key is it doesn't really matter what this solute is. The key is, as long as it's not another water molecule, as long as it's something with any kind of different shape, it's going to disrupt this crystal lattice structure. So in the same way, by the same degree. And that's why these colligative properties largely are independent of the identity of the solute. Any solute work, the only thing that really matters is which, what concentration do you have. The more particles you got, the more it's going to go down in the case of freezing point, the bigger that change in the colligative property is going to be. Now with boiling point, what in the world's going on that causes boiling points to go up? Well, let me tell you the lie, first off, that's often propagated. And oftentimes it says that the lie, is that when you put a solute in there, the intermolecular forces go up, and so the boiling point goes up. And that's totally a lie. It's not true. So it turns out what you really got going on in the case of boiling point, well, it turns out a substance is going to boil when the chemical potential of the liquid equals the chemical potential of the gas. And chemical potential are not terms we talk about a whole lot in Gen Chem. It's really more of a physical chemistry and more of an advanced topic. Just want to get you there first. But things like to be as low in energy as possible, so just keep that in mind. But when you're at the phase transition temperature, essentially what we're saying is that the liquid and the gas are equal in energy. It's kind of how we'll look at this term chemical potential. So they're equal in energy. Well, it turns out when anything that is spontaneous happens, it's always going to lower the energy of the system. So like if I let go of this marker, would we expect it to fly up to the ceiling or to fall to the floor? Well, it falls to the floor because that lowers its potential energy. And the same thing works with chemicals as well. When something is spontaneous and actually happens, it's going to be, because it resulted in a lowering of the energy of the system. And so typically, if you put a solute in water, it's going to dissolve, so assuming it's soluble. And so for putting a soluble solute in water and it dissolves, it dissolves, and that's going to lower the energy of the solution. And so it's going to cause this energy to go down for the liquid. And so at that same boiling temperature, these would no longer be equal. The liquid would actually be now lower in energy than the corresponding gas. Well, that's not when a substance boils. It only boils when they're equal. And so it turns out as you heat the liquid up, its energy does go up. And now you actually have to heat it up a little bit hotter than normal so that it's back to being equal to that chemical potential of the gas. And that's what's really going on. It's really related to entropy and stuff like this. So the entropy of mixing and all this. But it was really beyond the scope of this class. But I didn't want to just do some hand waving or tell you the lie or something like this. The truth is that when you've got this mixture, it lowers the energy of the solution, and you've got to heat it up a little bit hotter to get its energy back to equaling the energy of the gas, at which point it will boil, aka you have a higher boiling point. So if that went over your head, no worries. It's probably not something you truthfully need to understand for your Gen Chem class. So, but like I said, I just didn't want to wave my hands and say, oh, you'll get this later. You can't understand it. You're not capable. Didn't want to go there. So that is the deal with your boiling point. So, but we've covered freezing point depression. We've covered boiling point elevation. Let's take a look at Raoult's law with vapor pressure depression. Okay, so the next colligative property here, vapor pressure depression, depicted by Raoult's law here. And so Raoult's law says that the partial pressure or vapor pressure above a liquid solution here is going to equal the mole fraction of that particular liquid times its vapor pressure when pure. So, and the question we're going to look at here is, what is the vapor pressure of water at 25 degrees Celsius? Because vapor pressures are totally temperature dependent. But at 25 degrees Celsius above a solution containing 162 grams of water and 32 grams of methanol. And so on the previous page on the study guide, one of the constants for water I provided was that pure water at 25 degrees Celsius has a vapor pressure of 24 torr. And so you got a vapor pressure of 24 torr at 25 degrees Celsius for pure water. Well, if you have water that's not pure, there's less water down here. What that means is you're going to get less water up above the solution as well. So it lowers the vapor pressure, hence we call it a depression in vapor pressure. And so really ultimately the way this works, it's all about the mole fraction of water here. So if 80% of the moles down here are water, well then you're only going to get 80% as much vapor pressure as what pure water had. If 90% of the moles down here are water, well then you're only going to get 90% of the vapor pressure of what pure water had. And if you understand that in principle, you actually don't need Raoult's law equation. You'll just intuitively calculate those as percentages. Well, instead of percentages, we're actually going to be using this mole fraction, which again is the same thing as a percentage, but you're not multiplying by 100. So like a percentage of 90% would be a mole fraction of 0.9. A percentage of 80% would be a mole fraction of 0.8, so on and so forth. In this case, though, but we do definitely need to know the number of moles. And so if you're given the number of grams of the two components here, first thing you got to do is turn those both into moles. So we'll start with that water there. So we've got 162 grams of water. And the connection between grams and moles is again always that molar mass, and 1 mole of water weighs 18 grams. Pull out the calculator. So 162, well, that's not a 6. 162 divided by 18 is exactly 9 moles. I chose the numbers here to make them nice. And then 32 grams of methanol. So oxygen 16, carbon is 12, that's 28, plus the 4 hydrogens gets you to 32. And so having 32 grams of methanol, it turns out, is exactly 1 mole. That's not water, but of methanol. And so I made the numbers nice here. I made 9 out of the total of 10 moles water. That's 90% water. And if it's 90% of the moles are water, well, then we're going to get the vapor pressure of water above the solution as 90% of what it was for pure water. That's the way this works. So, but if we plug and chug this into the equation here, we can get the vapor pressure of pure water above that solution is going to equal 9 over 10 for that mole fraction. So 9 moles of water divided by 10 moles total, and then times the vapor pressure of the pure water, which was again that 24 torr. And 9/10 times 24, and again, if you want to do this in your head, you might think that 1/10 of 24, just move the decimal place back, is 2.4, and you might just subtract off that 2.4 to have the 9/10 that remain. And so in this case, that's going to come out to, subtracting off 2.4, 21.6 torr. Or if you like plugging that into your calculator, you can 0.9 times 24, and you'll still get 21.6 torr. So it turns out that Raoult's law, again, is typically for the major components. So if you've got two liquids like we do in this case, and the solute doesn't necessarily have to be a liquid, but if you've got two liquids in this case, Raoult's law will be most effective when your solute is really dilute, i.e. when your main component, the solvent, is really concentrated, if you will. So it turns out as you get more and more solute, finding the vapor pressure of the solvent in this case, you're going to find bigger and bigger deviations away from Raoult's law. So works really well for little tiny amounts of solute, but again, high amounts of solute, Raoult's law is not the greatest calculation, it turns out. We've got ways to get around that we're definitely not going to cover in this class, but you would cover in a more advanced class on thermodynamics. Okay, we've got one left here, and the one left will be osmotic pressure. So osmotic pressure here, and we use the Greek letter pi, analogous to our English letter P, but the Greek letter pi for osmotic pressure, so we don't kind of get it confused with gas pressure. So we don't use the letter P, but the Greek letter pi. And in this case, it's equal to the Van Hoff factor, so you still got to factor in how many pieces it dissociates into, if it does, if it's an electrolyte, times the molarity times R times T. Now, one thing to take a look here, again, many of you probably in your textbook, they'll have the I omitted, and you might just see something looking like this, MRT. And what they're intending you to do is have to factor in that, well, you want the total molarity of particles, not just the molarity of the solute, in which case you'd have to take the molarity of the solute multiplied by the Van Hoff factor, all kind of combined into that molarity. So just an FYI. And one other thing to look at here, if you take a look at this version of it, you can see that molarity is moles over the volume in liters. And if you rearrange this a little bit, you can get pi times V equals nRT. And hopefully that looks pretty darn similar to something you've seen before, PV equals nRT. And so for osmotic pressure, you can see there is some sort of relationship between it and gas pressure, as they kind of follow a similar kind of pattern in the way the equation might be set up, like the ideal gas law. So, but just keep in mind again that in this case, we don't use the letter P for osmotic pressure, that's gas pressure. We use the Greek letter pi instead. Okay, so let's take a look at what's really going on with osmotic pressure. And so first we got to talk about osmosis. And most of you probably know that osmosis from your biology class is the diffusion of water. And it's where water travels from an area of high concentration to an area of low concentration. When we say high concentration and low concentration here, we have to be careful because it's where water has a high concentration to where water has a low concentration. And if you actually looked at that in terms of solute concentration, well, water is going to be present in the highest concentration where the solute is present in the lowest concentration. And water will be present in the lowest concentration where the solute is present in the highest concentration. And so if you look at the flow of water here, it goes from where water is most pure to where water is less pure. But you could also look at it in terms of solute concentration, and students get a little confused about which one we talk about. And water is going to travel where there's lower solute concentrations to areas where there's higher solute concentrations. But the reason I looked at it in terms of water concentrations, because that's how we look at diffusion. Diffusion is the movement of something from areas of high concentration out to areas of low concentration. And so with osmosis being the diffusion of water, it's where water is going to travel from where it's most pure to where it's less pure, from where it's present in the highest water concentration to where it's present in a lower water concentration. And so the setup we have is this one right here, and we're going to have two compartments here. It's really one compartment that's divided by a semi-permeable membrane. And in this case, you can get different semi-permeable membranes. You can make them permeable to some things and not others. And what I'm getting is a semi-permeable membrane here that's going to be soluble to water and nothing else. Solutes cannot pass. So water can pass back and forth across this membrane, but no solutes can pass through. And so what we're going to find here is that we've got water most pure on the right, and then it's 1 molar NaCl. So on the left, which means again, pure water is 55.555 molar. So it was what we got over here. Well, if we got 1 molar NaCl, it means the rest of the solution is still water. It's still mostly water, but it's not pure water. And so we're going to find out that the water is going to want to travel from right to left, from where the water is most pure to where the water is less pure. If you kind of looked at that in terms of solute concentrations, though, you'd be looking at the water traveling from where there's no solute concentration to where there's a higher solute concentration. So just keep in mind, you might see it defined both ways, but again, I wanted to define it in terms of the water concentration, just again to make osmosis look as much like diffusion as possible, but don't get that backwards. All right, as the water wants to travel from right to left, what we're going to find is that the piston over here is going to want to rise, and the piston over here is going to want to drop. And the pressure I need to exert to keep that from happening is equal to this osmotic pressure. And so whatever pressure I have to push down on this side and pull up on this side, whatever pressure total that is, would equal to the osmotic pressure, which is again generated just due to the fact that water wants to travel a certain direction in this case. So let's calculate this out. And in this case, the question we're actually answering is, what is the osmotic pressure at 25 degrees Celsius of the fluid in this diagram? And so in this case, we've got a Van Hoff factor for NaCl of 2. The molarity was 1 molar. So R here. So in this case, I want to calculate this osmotic pressure. I'm going to do it in atmospheres, which is why I'm going to use the 0.08206 liter atmospheres per mole Kelvin. And this has served its purpose, so I'm just going to get rid of it. So I need that space, and then times the temperature, and temperature's definitely got to be in Kelvin, so that cancels there. So 25 degrees Celsius is 298 Kelvin. We see the kelvins cancel, and then the molarity is moles per liter. So you got moles per liter here and liters per mole here. They're going to cancel, and you'll be left with an answer in atmospheres. And so osmotic pressure has the same kind of units of all the other kinds of pressure that are out there as well. All right, so let's pull out our handy dandy calculator here, and we'll do 2 times 0.08206. Some of you guys, for that universal gas constant, might have 0.0821 rounded, either way. And then times 298. And we're going to get 48.9. Yep. There was a smudge on my calculator right where I was trying to read. So 48.9 atmospheres. And so in this case, the amount of pressure we'd have to push down on to keep the water from rising on this side and pull up on to keep the water from falling on this side would have to equal 48.9 atmospheres to keep those pistons from moving. And so my question for you is, well, what if I applied a pressure on this side downward that was only equal to 30 atmospheres? Well, then the water, due to osmosis, is going to be pushing up more than I'm pushing down, and it's going to rise on this side and fall on this side. Now, what if, on the other hand, the pressure I exert on this side now is exactly equal to 48.9 atmospheres? What's going to be the result? Well, nothing's going to happen because I'm perfectly balancing the osmotic pressure with the pressure I'm applying. Now, my question for you, and the important one here, is that what if, not 30 atmospheres, not exactly 48.9 atmospheres, but what if I push down with 100 atmospheres of pressure? And so I apply a pressure of 100 atmospheres. Well, osmotic pressure is only applying a pressure back of 48.9 atmospheres. So I'm pushing down with 100, I win. And I'm going to push this piston down, and that's actually going to force some of this water back the opposite direction as what osmosis wants to do. And I'm going to end up with more purified water over here. And hopefully you've gotten the gist here that by applying a pressure greater than osmotic pressure, I cause water to travel in the opposite direction of what osmosis would do, and I make more purified water. This is how your RO system, or reverse osmosis system, works. You're just going to apply a pressure that's greater than the osmotic pressure, so to create more of the pure water. Now, notice what happens is you don't get a free lunch here, because as you actually do this and you force more water off to this side, well, you're going to have less water over here, and your 1 molar NaCl is no longer going to be 1 molar. With the same amount of NaCl over here but less water, that concentration goes up. And as that concentration goes up, so does your osmotic pressure. And eventually it's going to reach 100 atmospheres, at which point everything's going to stop. And whatever concentration of NaCl you have in here, unless you're willing to apply even more pressure, nothing, no more purified water is going to be created. And so typically your RO system at home is going to have some sort of limit to the maximum pressure that's applied. And when you get to that point, the little bit of concentrated, solution you have over here is just dumped down the drain, and you start all over again, and can make more purified water with reverse osmosis. So that's how your RO system works at home. You guys should be prepared to do potentially a calculation with osmotic pressure, although I will say that's probably the least likely of these calculations you're going to see, but still a chance you might see it. But you should definitely understand the overall principle, be able to predict which way water is going to flow, things of that sort. Now, if you found this lesson on colligative properties helpful, so hit that thumbs up button. Best thing you can do to make sure YouTube will share this lesson with other students. And if you are looking for practice on general chemistry, my general chemistry master course incorporates over 1,200 questions. And if you're studying for finals, it also has final exam rapid reviews where I review all of Gen Chem 1 in 5 or 6 hours or all of Gen Chem 2 in 5 or 6 hours, and then also include practice final exams on top of that. For my general chemistry master course, I'll leave a link in the description. A free trial is available. Happy studying.